So we did a little bit of review before starting with the Gaussian beams. We wanted to derive or kind of remind you one more time how we get the spherical wave solution for 3D. And we're going to put it in cylindrical coordinates. And if you remember back from our first lectures, this is how the Fourier transform looks like. So in cylindrical coordinates, you have essentially a kernel that takes care of these coordinates in the k perpendicular magnitude and theta. Okay, and then the inverse Fourier transform looks like this. Along z, you still have the z coordinate. This is Cartesian Fourier transform, so it's one-dimensional regular Fourier transform, if you like. But in the xy, you get the J naught, the way we use it for the diffraction on a disk, for example, right? So that's how we put it in the cylindrical coordinates. So the idea is that we are going to look at beams that are actually, we defined the beam last time, right? The spread in K, in transverse K components is not too big. So it's much smaller than, let's say, the Z component. That's the definition of a beam. So for that, it kind of makes sense if you have an optical axis along Z to actually use cylindrical coordinates for X and Y. That's why we introduced this. And you can actually do the same approach. You plug it into here. You separate KZ from the K naught and K perpendicular. And you do the 1D Fourier transform along Z. Okay, so remember, before we were doing this, we separate this into K minus K naught plus K naught or minus. Yeah? So now, instead, we're separating the KZ component, the one that is in the Cartesian coordinates, and keep this, call that a new name. And I call it Q. But recently, I think I recognized that calling it QZ makes even more sense. So K naught squared minus K perpendicular squared, where K perpendicular is K squared plus KY squared, we call this QZ. And then, if you use that one-dimensional Fourier transform, I feel like I'm losing you guys. Is that true? So I can write this down as 1 over KZ minus Q minus 1 over KZ plus Q, where Q squared is K naught squared minus K perpendicular squared. So I'm just expanding that, right? Are you with me? So, as usual, we're going to look at the forward propagating one, so we'll just look at one term. And this becomes our old friend, one-dimensional Fourier transform of 1 over KZ minus Q. The one that gives us the plane wave, e to the I, is going to be e to the I Q times Z. So if you do that, this is exactly what you end up with. Yeah? So I have e to the I QZ over Q, J naught, the Bessel function. K perpendicular, this is magnitude, no longer vector, times R, K perpendicular, dk perpendicular. So this Q is actually, I'm going to discipline myself to call it QZ because it makes a lot more sense. Is actually a function of K perpendicular. Yeah? So that's why we have Z and then K perpendicular in the kernel, and then the integral over K perpendicular gives me back the function, the original function. So it's just another representation. So if we want to make a Gaussian beam approximation, basically what we're going to do is to approximate this factor, e to the I QZ over Q. E to the I QZ over Q is nothing more but the Green's function in the K perpendicular and Z domain, where the Green's function in R, meaning R perpendicular and Z, meaning in X, Y, and Z, in the spatial domain, this is our old friend, e to the I k naught R over R. So this is nothing more but the spherical wave in the k perpendicular and Z domain. It's just somehow is less common than this one. Everybody knows this, right? This is a spherical wave. If you represent that into the k perpendicular and Z domain, you get this. Because Q, remember, is square root of k naught square minus k perpendicular square. So it has k perpendicular in it. Yeah? So let's do our small angle approximation. And this is basically what we've done before. We've done this once before when we talked about the Fresnel approximation. How are you doing, Alex? Okay? If you need a coffee, let me know. So what we're going to do is to expand Q, which is this square root that we don't like, in Taylor expansion, right? So it's going to be, you take the k naught square out, it's going to be 1 minus k perpendicular square over k naught squared. Expand that as 1 minus k perpendicular square over 2k naught squared, and you end up with this. This is exactly what we did for the Fresnel approximation back when we did diffraction and the microscope and so on, right? Except we're in the k perpendicular and Z domain. So notice this, what this thing tells you is that if I have this beam, because I made the small angle approximation, it's implicit in this Taylor expansion. When I do this Taylor expansion and I say, let me write it one more time just to make sure everybody understands what we're doing. So k naught square minus k perpendicular square is exactly equal to k naught 1 minus k perpendicular squared over k naught squared. And now this is approximately equal to k naught 1 minus k perpendicular squared over 2k naught squared. And the approximation it applies whenever k perpendicular is much smaller than k naught. So this is exactly what you told me last time that the beam means, right? That the spread in k perpendicular is small with respect to the k naught. Okay, so what this means is that if I'm looking at the beam propagating along the optical axis, I can decompose it as a plane wave, this part, right? So this beam, this is the optical axis, is basically a plane wave and then some alterations on this plane wave, which is this second part. So the phase of this field is the phase of a plane wave that advances as k naught, and then on top I have this curvature, either this way or that way. That looks like this. This is a parabola, okay? So again, this is a Fresnel approximation in the frequency, in the k perpendicular domain. And we're going to say at the bottom here that Q, this is the amplitude part, remember? And we always are harsher with the amplitude term. They are less sensitive in a way compared to the phase. Phase is more sensitive. So in here we simply say, well, k perpendicular is negligible, take it out of the amplitude. This is a slow function, 1 over q, right? So whether I add this little bit in the amplitude doesn't make a huge difference. So I'm just going to replace it with a k naught, it becomes a constant. Yeah? Okay? When you do this, is the opposite of okay. You do this. Okay.
Why is it Q at the bottom in the denominator instead of R?
Because we are in k perpendicular. So I'm trying to force you always to think, first thing when you look at an equation, figure out which representation you're in. Okay? Am I in x, y, z? Am I in x, k, y, and z? Kx, ky, kz? I remember for me as a student, that was always a challenge because most of the books do not put, they write the electric field, but they don't put the variables in. So sometimes you get the, for example, you get the wave equation in space and time, right? And you can have the same equation in space and frequency, but of course it looks very different. So I usually carry the variables, except I didn't write that Q is explicitly dependent on K perpendicular. Okay? So if I were to take the Fourier transform of this to bring it to x, y, z, you will get back exactly what to expect. The spherical wave. Is that okay? We are in the K perpendicular and Z domain. We're not in X, Y, Z.
K and Z domain. Is it in K domain or in spherical?
Each coordinate you can have in anything. I can represent it in Kx, Y, and Z. It's not very useful, but I can do whatever I want. So it means this. If I go distance Z, and I take a measurement here, I can either put a camera and measure x, y, the field in x, y, right? Or I look at the angles at that plane, and I get kx, ky.
So it does the Fourier transform of x and y?
Yes, exactly, yeah. So I can do this independently. I have 4 coordinates, x, y, z, time, right? And I can choose, it's up to me which representation makes more sense. Yeah? So here I wanted to show you this K perpendicular Z representation, which is less common. But always look at, when you have an equation, especially when it doesn't have the arguments, the electric fields or any other functions do not have the arguments, try to figure out exactly where you are, which domain you're in. Okay? Okay, so you understand what this means. Expanding this, it means I have a plane wave that goes at k naught z in terms of phase, and then on top of it I have a k perpendicular squared, which means it's a parabola. This is a diverging wave, which means that on axis I have exactly, so when k perpendicular is 0, it means I'm on axis, right? No k perpendicular. On axis, I have exactly the phase of the plane wave. The moment I go off axis, k perpendicular non-zero, it's pulled back, it's delayed, right? So here it goes slower than the one on axis. Yeah? So it's the tangent between a plane and a parabola. Okay? That's what makes our image blurry in a microscope, if you remember. That Fresnel propagation, when this will be your kernel, right? So you get this curvature in your field, you convolve it with it, and it's going to blur your image. The larger the Z, the more the blur. Okay? Okay, so that's basically where the Gaussian comes from, because you have that K perpendicular square in there. Now, how do you get a perfect Gaussian beam in real life? Yes. Right. Yeah, so that's what we just showed, that if you take any point source and you let it propagate and you only look at the very narrow angle, you kind of get your Gaussian beam. True, but as you can imagine, that's not very efficient, because it involves you cutting a lot of the power, right? So you throw away most of the... So what, yeah. Use an oscillator. Use a laser. If your laser is aligned, the mirrors are well aligned. It should give you the 0 order, and that's a perfect Gaussian. Doesn't get any more perfect than that. The reason we filter the Gaussian beam is because you have other modes in it. Do you know what I mean by filtering? By passing it through a pinhole, right? So if I have, this is my laser, and somehow it doesn't give me a perfect Gaussian, but it gives me some kind of a messy beam like this. If I use a lens to focus it down, different Ks will be focused in different positions, right? This is the Fourier plane here. And if I place a small pinhole on top, I essentially only filter 1K out. So once I put the second lens in, excuse my drawing, you will get something that approaches a plane wave. Is not a plane wave because it's finite in size. It's going to give you some kind of a curvature. It's not a Gaussian because essentially what you measure is a diffraction at the pinhole. So this has to be a jink, except your jink is so fat, right, that if you look in the central part, it looks like a Gaussian. That's what we do with filtering. This is what we call spatial filtering. We do that all the time. But sometimes we overdo it. If your laser is great, there is no reason to do this filtering. Actually, if your laser is well aligned, you get the perfect Gaussian, there's no reason to mess with it. You will only make it worse. Once you put these edges in, the pinholes, so the pinholes are great, but they are edges. They give you diffraction. They give you a jink, this jink. So it's better to leave it alone if your beam is a Gaussian to begin with. Okay? Another way to do it is to actually couple this beam, instead of a pinhole, you couple it actually into a single mode fiber. And if your fiber is single mode, which means if your fiber is, the core is thin enough, there are some equations that define how thin is thin. But let's say for visible light, in the green probably has to be about 4 to 5 microns diameter for the core. That fiber will only sustain the zero order mode. That also will give you a perfect Gaussian at the other end. So why is it hard for us to make a Gaussian otherwise? It's because Gaussians means the wings fall off smoothly as opposed to being chopped off suddenly, like with the pinhole, right? Okay, so let's say one way or another, what we're going to try to show that one way or another we're going to get the Gaussian. And I want to understand if I pass that Gaussian beam through various lenses. At the end of the lecture, you should be able to compute any combination of lenses. You'll be able to compute how's the Gaussian beam looking after all those components. Okay, that's what we're trying to do. Because that's what goes in a confocal microscope. If you want to build one, you have to know, right, the size of the beam gives you the transverse resolution, the spread in Z. It's called the Rayleigh parameter. We're going to learn about it. That will tell you the actual resolution. So all these things you have to be able to calculate. Okay? So if you take the Gaussian, that Q factor here in the K perpendicular and Z domain, and you take a Fourier transform, it's very easy now. Take the Fourier transform with respect to R. This plane wave in the beginning stays like this. So this is really the Fresnel approximation that we did long time ago. And in R, it becomes a Gaussian beam as well. So meaning, if I look at the plane a Z distance away, I can, as I said, I can resolve it in X and Y, or I can resolve it in angle. So one is K perpendicular, one is X and Y. Both of them look Gaussian. Of course, with different widths, right? So in R, it's going to look like a Gaussian as well, like this. This is what defocuses your light in a microscope, right? Okay, so now let's say I have a Gaussian beam from somewhere. That looks like this. And I want to calculate how this propagates through various components. So for some reason, I have to say, most of the Gaussian optics has the Gaussian function without the 2 in here. I don't know why I decided to follow the regular notation. I would rather put a 2 in there, so this W becomes a standard deviation. But for some reason, most people like to define the width as 1 over, so when W equals R, you get 1 over E. So it's somewhere here. They call this W. I would have preferred it again to have a 2 here such that W, we can call that standard deviation of the Gaussian distribution. It will be more physical, but whatever. It's in the end, it's a detail. Okay. Now, I have a Gaussian beam of a certain width, W. I want to propagate it over an arbitrary distance, Z. So, according to my small angle approximation, I have to use my Fresnel approximated kernel H. Yeah? So basically, this is my input, U naught, at, let's say I call that Z equals 0. I want to figure out the field at a distance Z. So I need to do this convolution. And in order to do that, it's better to use the K-perpendicular approximation. Yeah? Because that becomes a product. So I take my field, my input field is this, e to the minus W squared, so the W naught goes at the top, and because we didn't put the 2 in the beginning, we now get the 4 in the bottom. Yeah? So this is my input field in the frequency domain. I multiply it with the Fourier transform of my Fresnel kernel H, which we found to be K perpendicular square over 2K naught with a Z in there. Okay? So you take this and you want to bring it back into the spatial domain. So I need to do this integral. If you do that, and I suggest you take half an hour and do it once in your lifetime. It's a little bit messy, but you can do it. It relates to the first homework where we had those 2 Gaussians, convolution of 2 Gaussians, right, with the input and the impulse response. That was kind of, is the same thing. So you get 2 Gaussians. You expect that the width is going to broaden, right? And we know exactly that the variances are going to add. Okay, so that's something nice. But at the end of the day, you are going to end up with this. So the plane wave notice Z plays no role in the front here. It plays a role somewhere in the width of the Gaussian. So you end up with another Gaussian, first of all. Except this width now has both real and imaginary parts. And there is a normalization constant, C squared. The same C. What's the meaning of this width having both real and imaginary parts? What do you think? Which one?
Usually imaginary ends up being the attenuation.
Except I didn't put an I here. So if I had an I, these will change. This will have an I, this will not have an I. Okay? But doesn't matter the convention. The attenuation part comes from the fact that as the beam expands, so it propagates, it diffracts, right? The power has to go down at each point, right? To conserve energy. That's what that means. And then you have the phase term, which is this one, which is telling you exactly how the wave is delayed at each point, right? As the beam expands, the Gaussian gets fatter and fatter. Essentially, the delays across are getting closer together, right? So when you have a tighter Gaussian, very narrow, immediately as you move away from the optical axis, this is going to be delayed more than along the optical axis. Once the Gaussian is fatter and fatter, they're kind of going more slowly varying as I move away from the axis, right? It's a smoother phase variation. Okay, so let's talk about some definitions. So basically, this is the full solution, which is okay. You calculate it once, it's good. Now, what I want to do is to find some really useful procedures for passing this Gaussian beam through a bunch of optical systems, in particular lenses. So first, let's introduce some definitions. So notice here, I'm going to write this as Z over Z naught. So I factored out W naught squared, and then it's going to be 1 plus I 2Z over K naught W naught squared. Ta-da! So what it says is that I started with, this is my input. This is a Gaussian of width W naught. Yeah? C is telling me how this W changes, basically. Right? So when Z is 0, I'm basically at the input, but my W becomes C. As Z grows, I'm going to write it as Z over Z naught, where this Z naught actually has a name. Okay? This is going to tell you basically the distance over which W goes up by square root of 2. Okay? It's going to become apparent in a second. This Z naught gives us a scale of how fast that Gaussian grows, right? That's the meaning of it. So, for example, to get a feel for it, if I have a very tight lens, very tight focus with a microscope objective, right? Very fast. You expect Z naught to be big or small? Very short, right? And if I have large focal distance, the focusing is going to be very mild, right? So that's what it means. So this is called Rayleigh parameter. And it has a very interesting explanation too. Or another interpretation that I like. I kind of like it. So imagine, so we're talking about this kind of a beam, right? This beam is expanding. This is Z equals 0. This is my optical axis. And let's say this is Z naught. So if I take a cross section through here, let's say this is W, this is W naught, and W is actually square root of 2 W naught. So the interpretation of this Z naught is the following. If I take the area of the input beam, is the distance Z naught over which, if I cut a rectangle of width lambda, that rectangle and the input area are the same. That's how I remember this formula. You know what I'm trying to say? So I have an input area, transverse area of the beam defined as pi W squared. That's a disk of radius W naught. Z naught is the distance over which, if I make a rectangle of width lambda and I multiply with Z naught, I get the same area. So lambda times Z naught gives you an area of the rectangle that equals PW naught square, which is the area of the disk. So now you remember that formula. I don't need to memorize. Okay. So, okay, Z0 is called the Rayleigh range, as I mentioned. And there is something very interesting that happens to the beam. So, there's these obvious things that we mentioned already. So the beam spreads, W grows, the power goes down because of that, right? But there is also something very interesting to do with the phase of the beam. So, you can write this C, the complex, this complex quantity, as W squared as e to the I psi Z. So basically that psi is the argument of Z over Z naught. So it's kind of the arctangent this gives you a phase, we call it psi. Sorry, psi, like that. This is called the Gouy phase. From a person named Gouy, French, who discovered this effect more than 100 years ago, or about 100 years ago. Meaning, let me explain what it means. If you write the complex field, all the formula that we derived earlier, what do you get? You get an exponential amplitude decay. So, as I said, the beam, the power goes down. If you take an intensity profile, it's also Gaussian. Or an amplitude profile is also Gaussian. No surprise there. You get your plane wave, the one that kind of tells you the phase shift on axis. You get the Gaussian phase change. That's not surprising either. This is what's surprising. That you get one extra phase. And this is what is called the Gouy phase. What it means is that if I take a beam and I focus it down, I take a Gaussian beam, focus it down. I think I must have a... There we go. Imagine I take a Gaussian beam, focus it down, and then I let it propagate. W naught, I get W here at Z naught. If you plot the Z profile of the phase right underneath of the Gouy phase, it's going to look like this. What's our tangent when Z equals Z naught? What's our tangent of 1? Okay. So when Z equals Z naught, you get arc tangent of 1 equals pi over 4. And arc tangent, when I go to the minus sign, I get arc tangent of minus 1 equals minus pi over 4. So basically, this should be 4 pi over 4. As I go in from minus infinity, my Gouy phase does this. So I have a phase that looks Gaussian, and it kind of the width of the Gaussian goes down as I propagate in Z. But to make everything work out, in particular to have the energy conserve, you have to have this phase in there. That there is a slight change out of when you're far away from the focus. But then right there on the focus, you get the huge... Oh, I know why this didn't make sense. Hold on. Because it has to be... So here's what happens. That's pi over 2. This is minus... Oh, I'm sorry, 4. All right. So This will be pi over 4. This corresponds to z naught. Minus z naught, another pi over 4, negative. So that's minus z naught. But it continues to grow to pi over 2. Okay, that makes more sense. Because altogether should be pi. So right around the focus, this transition becomes steep. There's a big change in phase as you pass through focus. And this was very surprising, especially back in the day. And I think it's still, there's still people publishing on this today, because it's kind of an interesting phenomenon. The way I look at it is like, it's all due to the curvature of the beam. Okay, so it's surprising in a way because people usually deal with plane waves. So you have a plane wave this way, that's k naught z, another plane wave, another k naught z. When you put many k's together, the problem is that there is an average kz that plays a role actually. That you have on the z-axis, you have contributions from all these components of the k vectors, and the average of that k vector is no longer k naught. It's not acting as a plane wave of wave number k naught. It's actually slightly shorter. It's only on axis that the beam acts as a plane wave of k naught z phase, right? As I move off axis, my kz component is actually slightly shorter than k naught. And then the higher the angle, the shorter the kz. So essentially, on average, that kz is smaller than k naught. You're missing some phase as you propagate through. And when you reach the plane of focus, yeah, when you are here, what's the curvature there? What's the curvature of the beam? Infinity. It's a plane wave. So you see? So you have k vectors going this way, and then here you only have one k vector. That becomes k naught again. That's why my GUI phase actually is 0 here. I don't have that curvature effect. And then I go through it, I go on the other side, and I get the divergence guide. So I came in convergent, and now I'm going divergent. So now I lose the kz, the average kz becomes smaller than k naught again. So I have to compensate for that. That's where the GUI phase comes from. So it's not really, in the end, it's nothing magical, but it should be there. Okay? So it's because your kz is getting slightly shorter than k naught. All right? I think we're going to get to that in a second when actually we're going to show that this, because of the GUI phase, we get the phase velocity that's bigger than c. Is that possible? Okay. Well, we'll get to that in a second. So here's the amplitude of the field. 1 over W. W can be written as the original W, so the input beam waste. This is called sometimes waste. 1 plus z squared over z naught squared. A Gaussian amplitude, it tells you the attenuation. And the phase that has the plane wave, it has the Gaussian phase distribution. And then you have the GUI phase, which is this one. At the bottom of this Gaussian, you have R of z, which is called curvature. Okay? So let's talk about that for a second. So the curvature of the beam is exactly what it sounds like, right? It tells you the radius, the local radius of this wavefront. Notice, when my distance is very, very high, when I measure very far away from my input, the curvature is the same as z. What does that mean? R becomes Z. Spherical wave. Because it's a curvature. So you still have curvature, but it's constant. It's exactly equal to Z. Yeah? So basically what it means, if I go far away from this plane of focus, my plane of focus becomes a point. And my spherical wave is defined with respect to that center. Interestingly, in real life, when you have a Gaussian beam, the center of this circle, if you want, is not exactly in the middle. It's actually offset. For the same reason, that the GUI phase shows up, is because my KZ is not exactly K naught. This is actually offset a little bit, which actually, it's interesting. So basically, if you have the curvature of the beam and the beam waist, the W, pretty much you characterize that Gaussian beam perfectly. So in the end, what you want to be able to do is that if I put a number of lenses or any optical components, I want to be able to calculate, to predict how W and R is going to look at the end. So if I put input R naught W naught, what's my RW at the end of the day? That's our goal. Well, there's one more parameter that is very commonly used. We use it all the time. The diffraction angle. How do we define the diffraction angle? Well, intuitively, is this tangent. Imagine this being the locus of the beam waist. That's what this curve means. Okay? So I'm plotting the width of the Gaussian. Right? So if you draw a tangent from the center of the focus to that curve, you will get an angle. That is what we call a diffraction angle. So notice, when you get to the details of the things, defining an angle, defining the beam width or waist, all these things require a little bit of careful definition, right? So in particular, the diffraction angle is basically, so this width, W divided by Z, but it's only well defined for very large Z's. It's only well defined for large distances. Okay? So that's kind of important because it's a limit. So when you draw that tangent, you have to be far away from it. So if you take a laser pointer or any laser and you try to define a divergent angle right at the input here, that's not great. Let's put it that way. Okay? Okay, so is W over Z naught or is lambda over PW naught? Okay. So we have radius, we have waist, and we have theta, but this is comes out of W, so it's not, once you know the wavelength and W, theta just comes out. Okay? So it's only two parameters that we care about in Gaussian beams. You can calculate everything else. There we go. So here's my picture with a GUI phase. Okay, let's talk about the phase velocity as a fun fact. Definition of the phase velocity is omega over k, temporal frequency over wave number. Yeah? The problem is we have a bunch of k vectors, right? Gaussian beam has a distribution of k vectors. It's narrow, but still, it's not a plane wave. So in order to, that's why I wrote here k effective, or k average. So in order to compute the k average, you need to take the derivative of this, of the phase term. So we had the plane wave and we had the azimuthal. We don't look at the Gaussian part. So the plane wave and the GUI phase. If you take the derivative of that, this will give you an effective wave number. It tells you how fast the phase changes with respect to z, right? So this is the phase of the Gaussian beam. If you do that, clearly you get k naught first. So that's obviously, this is the wave number of the plane wave. Okay, so omega over k naught is going to give you exactly the speed of light in vacuum, by definition. But the interesting part happens here. When you take the derivative of psi of z, you get 1 over z naught, blah, blah, blah. You get this one. You get a number that is slightly smaller than k naught. And when you take the ratio, omega over that is going to give you a phase velocity that is slightly higher than the speed of light in vacuum. Is that the problem? No. There is no problem. You can have phase velocity much higher than c without breaking any relativity theory. It turns out you can actually have group velocity higher than c too, without breaking the laws of physics. What you cannot have is a signal velocity, the velocity at which you can send signals higher than c. That is capped. But phase velocity is very easy to do, to make it higher than c. I mean, you just focus the beam down and watch it expand. That gives you a phase velocity higher than c. You cannot encode information with that velocity, unfortunately. Okay? All right, so in summary, what did we do? We approximated the solution of the wave equation. I wanted to show you how to do it in the cylindrical coordinates because that's what applies to beams. Okay, so we ended up with that q as a function of k perpendicular, which I like. So you can write your wave in terms of k perpendicular and z. We made the Fresnel approximation, or the Gaussian approximation to that kernel, right? And then we took a beam. We said, I don't care how we generate it, but I'm generating this Gaussian beam, let's say by a single mode laser, with this input waste W naught, okay, and the Gaussian distribution. I want to know how this is going to look like a z distance away from my input. We convolved the input with the impulse response with my Fresnel kernel. We came up with a formula. I didn't show all the derivation, but again, please do it once. And you end up with a formula that now has Gaussian form in amplitude, Gaussian form in phase. It has a plane wave in phase, also a phase term there, that we know what it means. And then it has an interesting extra phase term, which we call the GUI phase. And I hope I gave you an intuition why that should be there. And it's because of the fact that the phase advance along z is not simply k naught. It's actually smaller because you have these projections of the k vectors, off-axis k vectors. Their kz projection is slightly smaller. It's k naught cosine of theta. So while cosine is a lazy function for small angles, nevertheless it is not constant, right? So that's where the GUI phase is coming from. So at the end of the day, we have a beam waist, W, where is it? This one. That looks like this. W naught plus z squared over z naught squared. So z naught is the Rayleigh parameter that tells you the distance over which W goes up. W squared goes up by a factor of 2. 1 plus 1. Or when the beam waist goes up by square root of 2. So that's my waist. And then the radius. Where is it? Here. This is the definition of the radius. Okay? And then we define the diffraction angle, which is basically W naught over Z naught. So if you know W naught and or W and Z, or the wavelength of W naught, you can retrieve theta. Okay? So next, we are going to find a nice way to calculate R and W, the curvature of the beam, and the beam waist, in an arbitrary number of lenses, for example. Lenses and free space propagation. So basically, if we know how to propagate light through free space and through lenses, we can make any system that we want. Microscopes, telescopes, anything. So we are going to define a matrix formalism for geometrical optics for small angle approximation of wave propagation. We did this formalism back in ECE 460. But I'm going to review it here. It's kind of interesting. It's the same matrix formalism that gives you the ray propagation in geometrical optics. Those same matrices apply just as well to Gaussian beams. So in geometrical optics, you get basically the elevation of a ray at a certain plane, what's the distance with respect to the optical axis, and the angle of the ray. These are the two parameters that tell you everything you need to know about a line. Angle and where it hits this plane, right? So those matrices help us with that. We did that in 460. Here we show that actually the same matrices that apply to lenses and free space will give us R and W for Gaussian beams. Clearly, it's not so surprising because they're both small angle approximation. So it's essentially linearizing the problem. So linearizing those square roots and stuff. That's why the matrices apply, because it's a linear problem. Okay, so let me review quickly the matrices for a ray. So if I have a ray here, y1, and I'm looking at the z distance away, y2 is going to be the same. Theta, I'm sorry, y2 is going to change, but angle is going to be the same. So I can write y2 as y1 times the distance times theta 1. So you see what I'm doing here? Just geometry. So it's going to be y1 plus d times theta, where this is d. Yeah? And theta is the same. Theta at this point and theta at this point. There is no bending in the rays, no change. So I write it in a matrix kind of formula. So y2 equals y1 plus d theta 1. Theta 2 equals 0 times y1. So it doesn't depend on y1. Plus 1 theta 1. So I can write my matrix as this. 1, 1, d 0. So I can write y2 theta 2 equals this matrix times y1 theta 1. This is identical to that. So it means whenever you need to propagate a ray over a distance, arbitrary distance d, you just take your input. This is an input vector, right? Multiply the matrix, and I get the output vector right away. Okay, that was easy, right? How about refraction? How about I have a ray at this interface separating two refractive indices, N1 and N2? Well, what's the law that describes this? Snell's law. And we're going to again approximate sine of theta with theta. So Snell's law says N1 theta 1 equals N2 theta 2. By the way, this is a wave vector law. Did you know that? Yeah? What does it mean? What does Snell's law mean? Phase matching. But in terms of momentum, in terms of K? Momentum conservation. So what does it tell us when I say N1 sine of theta 1 equals N2 sine of theta 2? Tangential, wow, we have experts in the room. So if I multiply this by omega over c on both sides, I get that k, basically k1 along this, let's call that x, let's call this z. So along x equals k2 along x. Why? Because my k vector is this, k vector at k2 is this. The projection will be k2x. Projection here will be k1x. Snell's law says that these two should be equal. The in-plane, the tangential at the interface. Right? Which is, doesn't it remind you of the mechanics problem? When you bounce a ball on a plane, remember in high school? You bounce a ball in a plane. Momentum conservation only has to do with the normal, right? If there is no friction and there is no weird spinning of the ball and stuff, there is nothing that happens in the x and y plane, right? So it's kind of the same thing. The contrast in the refractive index happens in this direction. This is the gradient of the refractive index. So the change happens in the normal component of the k, nothing in the tangential component. Is that nice? Thinking k domain, it will save you a lot of trouble. Anyway, so now that we know Snell's law, we can move on. So n1 theta 1 equals n2 theta 2. So we approximated the sign with the angle itself. Now, it's the opposite situation. Theta changes, but y doesn't change. Right? So I'm looking at the ray in, ray out, so without any propagation. So y is the same. So y2 equals 1 y1 plus 0 theta 1. Right? So I get this matrix, 1, 0, 1, and 1 over n2. Yeah? Nod your heads. Okay. Propagation through a thin lens. This is the symbol for a convergent lens. So if I take a, remember we did this when we talked about microscopes, right? So if you take a ray through the center of the lens, nothing happens. So that's one ray. If I take a parallel one that hits, I don't know, hits my lens at the elevation y, I know it's going to be focused in the focal plane because I know this is where the Fourier plane is, right? So we are beyond geometrical optics with our course, right? We know this is a Fourier plane actually. We even understand that this is not an infinitely small point. This is actually blurred by diffraction, right? So we did all that. But we know that it's going to focus at this plane, which is a focal distance away, f. And it's going to meet the ray that went through the center because all of these parallel rays are going to be focused in the same plane, right? Because that's what lenses do. They do a Fourier transform. They map angle into a point. So I know that all parallel rays incident on the lens, they're going to be focused into a single point. How do I find that point? Well, I draw the one through the center because I know that doesn't get bent. Is that okay? Good. So now my problem is easy. So I was trying to figure out the bend. Again, I'm talking about the ray just before the lens and the ray just after the lens. I'm not looking at the propagation distance. So y, again, y is the same. It's only this angle that changes. How does it change? Well, my angle theta 3 is, I have to look at this distance. So it's this distance, which is y plus, no, it's this. It's f theta 1. This is my y. And then I subtract my high school geometry kicking in slowly. So I'm calculating this little thing, delta y. Because my theta 2 is going to be delta y divided by f. And delta y is the big Y from here to here, which is f theta 1 minus this portion, which is my input, y1, divided by f. So it's theta 1 minus y1 divided by f. Okay. Yeah? Are we cool? All right. So I end up with another little matrix. 1, 1, 0, and now my f moved to the off-diagonal bottom term. So now guess what? This is the third matrix. So the free propagation one, or the translation if you like, was number 1. The refraction, number 2. And now the lens is number 3. I understand everything if I know these 3 matrices. Because anything you throw my way, I will be able to write a matrix for it. For example, what if you're building a confocal microscope and your advisor is telling you that here's the lenses and I drop in for no reason a beam split or this block of glass, I don't know. Calculate what comes out. How do I do this? Well, from here to here, I calculate with the translation matrix. At the lens, I apply the lens matrix. From here to here, I have another translation matrix of a D2. Here I have a refraction matrix at the first interface, then propagation through the block over distance D3, refraction outside, another lens, another refraction matrix here, another free propagation here, another lens matrix here, another free propagation here. I'm done. So if you don't use the matrices, this may seem like a nightmare, right? I mean, it is. But if you put the matrices in your Mathematica or whatever, it becomes simply a matrix multiplication, and they're all 2 by 2, and they have a lot of zeros. Still, it's a nuisance to do by hand, but if you plug them into your favorite program, it's really easy. So output equals input times, that should be theta 1, right? Times this whole thing. So multiplying 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 transformations. The only thing that can go wrong is the order of matrix multiplication. So what's the order? I call this chronological. The matrices have to be multiplied in chronological order, and by that I mean the following. If you plot, let me try this. Okay, so I want you to look from here all the way to here. So D1, the matrix of D1 appears here, but D1 appears on the left. So if you look quickly, it may look like the matrices are multiplied in the wrong order, right? But they actually, this is the correct order. Why? Because MD1, the D1 matrix should multiply my input first. That's what I mean by chronological. Then I get what happens next to my vector. It happens the lens 1, and I do this. And then what happens next and so on. So I should end up at here with the last matrix that happened. And as you know, matrix multiplication is not commutative, right? So it's very important that you actually get the correct order. But once you make sure of this, then it becomes a breeze. You can go crazy with the number of components. It doesn't really, it's going to be instantaneous with a good computer, right? Do you have any questions about this? Because we linearize the problem for small angles, cascading optical components means matrix multiplication. Okay, so the question that remains is still, what is this to do with my Gaussian beams, right? So if I call the entire matrix for a system, like the previous one, I had two lenses, air, and a cube in the middle. If that whole thing, made of 9 individual matrices, if I combine that into one matrix, some people call it ABCD matrices, so let's name them like that. So ABCD, these are the elements. Here's what happens. Let's call this your black box, characterized by matrix M. I put in a beam of waist W and radius R1. I'm trying to understand what comes out. W2. Yeah? It turns out that I have to define one, this is Q, not G. I mean, you can call it whatever you like, but in most books it's called Q. If I define this Q, it's called complex beam parameter. Essentially what I'm trying to do is to combine the radius and waist into one quantity, Q. And to make it count as two variables, basically it has to be complex. So if I put 1 over Q as 1 over R plus I lambda over PW naught squared, so this is the Z naught, I make a complex thing that completely characterizes my beam. Then, ta-da, these are all Q's, I'm sorry. So Q2 equals A Q1 plus B over C Q1 plus D. This is the big deal. Now once you have the input Q1, 1 over R plus 1 over plus I over Z naught, the output, once you calculate the matrix, the output is simply this. That's it. Do you see the power of this result? Because now you can throw in indefinite number of lenses, surfaces, distances. So you multiply all the matrices in the proper order, and then at the end you just do this. It will give you automatically the beam out. Cool? Alex is excited. He pulled all-nighter last with the homework 4, so it's my fault. Okay, so let's do an example. So let's see. Oh, here's a very practical, I thought of a very practical example. Sometimes when we design a setup, we have various constraints, right? You may want to have a microscope that has to fit into something. Yeah, definitely you don't want to be outside of the lab measuring stuff. So that's one constraint. Keep it inside the lab if possible. But sometimes it's even worse, like I have to fit into this box or I have to fit into this other instrument, right? So here's an example. I have an input beam, so let's read the problem. Gaussian beam of this much divergence is focused down by a lens to half of its minimum waist. So I have an input waist, I need to half that waist with this lens. But it has to be done within a distance of 1 meter. So this is a very practical thing. I have, this beam waist is too big for my purpose. Okay, I needed half that. Okay, but I don't have a lot of space. So I need to use a lens, make this beam twice smaller, but it has to be within this distance. I said 1 meter, but whatever. All right? So what lens do you choose? So you pick up the phone, you call Thor Labs. What do you ask for? All right. So I don't think you don't know this if you didn't take 460. But to compute the matrix of this system, you have to have 1, 2, 3 components. Free space from here to here, lens matrix, and the free space matrix again, right? It turns out that if you do that, and you call this D1 from here up to here, and then you call this D2, where D1 plus D2 equals D, that matrix looks exactly like this. What does this look like to you? Anything? The lens equation. Not the lens maker, but yeah. But do you recognize it? It's kind of interesting, actually. It's my favorite way of deriving that equation that tells you if I have a lens, where is it producing an image? Very simple question, right? So let me show you where that is coming about. So if I have m times y and theta, it gives you, so ay, okay, so it gives you y prime equals ay plus b theta, and theta prime equals cy plus d theta. Yeah? What is the condition for imaging?
Theta goes for any theta, y is the same.
There we go. So here's the condition for imaging. This formula, this matrix works for no matter which ray, arbitrary. Could be the image plane, but it could be any. Let's say this is my sample plane and this is my image plane. But the matrix formalism works for any plane in between. I can look here, 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 anywhere. But in the image plane, what happens is that if I take all these rays from one point in the sample, they all converge in the same point, no matter what this theta is. That is the condition for imaging. That all the rays that come out of a point at the sample will converge to one point at the image plane. That is the definition of imaging. Any other plane, look what happens. For example, if I fix my plane here, I'm going to get that different thetas have different y's, right? They're spread. So if you image in an autofocus plane, that's what you get. If you have aberrations, that's what you get. This matrix covers all the cases. It doesn't care. You pick a ray, it's going to give you where the ray is at any plane here, okay? So what changes is your D's will change. But the condition for imaging is that y prime depend on theta, which means that D has to be identically 0. So if I go in my little element B, what I get out is if I divide by D1, D2, I get 1 over D1 plus 1 over D2. Let me make it big, it's important. 1 over D1 plus 1 over D2 equals 1 over F. This is the imaging condition for a lens, or the lens formula. So if you give me a focal distance, there is an infinite combination of pairs of object and image that I can come up with, right? If I fix the object distance D1, then D2 becomes fixed. If I make D1 go to infinity, my light is parallel to the optical axis. The image is going to be at D2 equals F. So an object at infinity, a plane wave coming in, is going to be focused at the focal plane. If you make D2 infinite, you get D1 equals F. So if you go from the other side. Okay, back to our business. So now, hopefully you believe me without proving that this is the matrix for air, lens, air combination. So, this is Q. All of them are Q, no G's. Since I know that I'm at the plane of the waist, minimum waist, okay? Minimum waist is where the beam has what curvature? You told me earlier. Infinite curvature. Yeah? So when I calculate the Q, which is 1 over R plus 1 over plus JZ naught, plus I over Q equals 1 over R minus I over Z naught, isn't it? Like that? Plus we cannot have it both ways. Okay, so when R equals 0, I'm sorry, this is 1 over Q, right?
Online it's minus.
Huh?
Online it's minus. Unless you move higher.
Here is minus? This is minus?
Yeah, with the imaginary component upstairs, numerator.
So then Q becomes I Z naught, right? When I flip them over. When I flip them over, this becomes 1 over I, which is minus I. So, I mean, when you say online, what do you mean? Like a blog of some undergraduate who's had an all-nighter, or?
The complex beam parameter Wikipedia article.
Okay, so this is a minus?
Yeah.
Okay. I think that is true. So this should be a minus. There we go. Okay, so when you are at the minimum waist, that radius goes to infinity, so your Q is very simple. So Q1 is I Z naught 1. Q2 is I or J, I don't know why I switched to J, Z naught 2. I think it's the student who helped me type this up. Okay? So now I have a relationship between the two, which is that Q2 equals AQ1 plus B over CQ1 plus D. So remember what we want to say is that W naught 2 is half of the W naught that I put in. Okay, so after you do all this, you plug it in, blah, 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 you get the focal distance that gives you this. So I'll let you have fun with that. And it will also give you the D1 and D2, clearly. We know their sum should be 1 meter, but I have an infinite combination of pairs that I can have, right, of D1, D2. But since my waist has to go down by a factor of 2, that will uniquely lock it in place. Okay? Good. So that's pretty much all I was planning for Gaussian beams. So to review everything, we can write matrices for free space, for lenses, for refraction at an interface, and in combination you can pretty much solve any problem you can think of, right? Passing Gaussian beams through any components. And the beautiful thing is, at the end what you have is that this matrix ABCD for the combination connects the two Qs. Q1 to Q2. And basically the Q, these complex beam parameters, is wrapping in both parameters of the beam. That's why it's complex, to have basically two variables, the radius and the waist. Okay? So that's it.